Ouais, la clé.
Elle est où cette caméra? Ah, là-bas. Et alors, du coup, et les gens, ils suivent sur Zoom ou sur YouTube?
C'est YouTube, normalement. Il n'y a pas Zoom. Je sais pas.
Si, il y a Zoom aussi. Parce qu'il y a des gens qui se connectent sur Zoom. Ouais, il y a des gens là qui font ça. Comme Massive MIMO, tu Massive Vote.
En fait, c'est des nouvelles de
Non, 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 il est à la revue. Ça devrait... Ouais, ça devrait aller. Hein. Qui est là-haut, là? On descend là-haut.
Le truc, c'est.
Attends, c'est le méta-surface 2022, je crois.
Installer mon micro.
Si, grand thème, méta-surface 2022.
Grand thème.
Ouais, je crois. Yes.
J'ai vu Laurent Sandra hier.
Ouais. Laurent Sandra. Oui,
On
Laurent.
vous installe un petit micro. Très bien.
Installe. Je vais vérifier juste qu'il est connecté.
Timothée?
C'est bon.
Alors après, je ne sais pas si vous l'ouvrez dans l'eau.
Parce que j'avais déjeuné avec lui il n'y a pas longtemps.
Il y a quoi? Il y a un petit clapet normalement pour mettre sur. Il y a des caméras et tout. Ouais, il y a tout.
On va mettre comme ça.
Ah ouais. Il ne faut pas que je dise de bêtises là.
Ouais,
il a été Mirwan. Celui-là. Ouais, celui-là 23 là. Et très bien.
Ouais, mais de toute façon, moi j'avais bouffé avec lui, c'était intéressant.
Et combien de temps j'avais là?
Comme d'hab, 3 quarts d'heure.
3 quarts d'heure, ok. Ça, je peux passer vite.
Je vais t'introduire d'abord au départ.
Enfin, ne m'introduis pas quand même.
Et c'est sur YouTube, c'est sur.
Alors, au lieu de me dire je vais te présenter, mais je vais t'introduire. J'ai dit le mien, je vais te présenter, il me dit je vais t'introduire.
Ici?
J'ai dit très délicat comme.
Ça dépend des langues.
Hello.
Vous êtes en ligne.
You're online. What? So everybody has your information, Misha. On est bon là, JB? Shall we start?
Yes.
Oula.
On passera un micro.
Okay, so hello everyone. So today is the second event that we organize, which is called Greenerwave.Focus, organized by Jean-Baptiste. Many thanks, JB. So the idea of these events is to bring together people from various fields, and both from academia and also from industry and from startups. And the idea is to share some knowledge on various topics, which are of interest, of course, of the company. Today we are very happy, and I'm super happy to have rouane Debbah coming to our new offices. So I met rouane, I think, more than 10 years ago on Mauritius Island. It was a very nice conference. We went together. rouane is let's say, super well-known and talented scientist in the field of wireless communication. So brief bio of rouane. He is a former student of École Normale Supérieure, and he spent some time in various labs in the beginning. I think so you got your PhD from École Normale, and then you went to Vienna, and you spent some time as an assistant professor in Eurecom. Then rouane went to Centrale Supélec as a full professor. He was working at the time on small cells, then on massive MIMO, random matrix theory. And then rouane was appointed by Huawei to start a research center, the research center of Huawei in Paris, which he started, and that is going super well now. We also started a few years later the Lagrange Center, which is a research center for mathematics and wireless communication. And now rouane is at TII, so Technology Innovation Institute in the Emirates, and is again starting a new research center on wireless communication, and is very interested now not only on massive MIMO but also on smart electromagnetics environments and large intelligent surfaces. So the kind of things we are doing here. So we are super happy to listen to what rouane is going to tell us about that today. Thanks, rouane.
Thank you for the introduction. It was very good. So I'm very happy to be here. I've been following Greenerwave since the beginning, and Geoffrey and Matthias know this also. On even when I was at Huawei, positioning the company Greenerwave at the start of all these, I would say, large intelligent surfaces, reflected intelligent surfaces, smart controllable surfaces, whatever the name you give it. And I think I saw the evolution of this company, and I'm quite very well impressed by how things have been going on. And one of the reasons I came to give a talk is, of course, also that I strongly believe in the work being done here, and in terms of also its application in telecommunication. And here, the purpose of my talk is mostly to show that most of the things that you're doing is getting a bit of momentum in telecommunication field, and will have, I would say, more or less a big impact in what we call 6G, okay, and which is also rising quite heavily. Was there a problem with the sound? Okay, good. Then it's fine. And so that's the first thing. Second is also the place where you're here. I came here a couple of years ago, but it was mostly about hackathons, which were organized by Huawei. So I remember well this place many years ago, and it was organizing some hackathons during more than 24 hours coming here, and which is also a very good place to come back and see how things have changed in the right way. So as far as I'm concerned, so I worked in the discipline of telecommunication for many years, and I've been working at the interface of what you call mathematics, physics, AI, 6G, and I've been running a lot of things between industry and academia and these things. As far as I'm concerned now, I'm working for an institution called the Technology Innovation Institute, which is basically a new initiative brought by the Abu Dhabi government, which is one of the Emirates in the UAE, which is strongly investing today in the transformation of what we call the the oil-based economy towards the knowledge-based economy, and looking at building some kind of huge capability in terms of scientists in Abu Dhabi, similar to what you would have as a Fraunhofer Institute in Germany, A-Star in Singapore, KAIST in South Korea. These are the kind of models on which we're working, with a center which is working on a broad range of basically domains, which has also more focus on applied research. Okay, in the sense that we are very use case driven, and as you know, when you do use case driven research, it can be technology driven or business driven, and depending on the clients you have. And this is the kind of mixture that we're trying to have, where we're having like roadmaps which go on from an 18 months perspective to things which are more 6 years, which could be related to 6G. Things around the UAE, which could be of interest for you. There's a big transformation of the country in terms of investment and where it's going. And you have to know that today it's one of the most innovative economy within the Middle East and North Africa, sorry. And in the sense that Israel is number one in that region. And then you have Turkey. And then the third one is the UAE. So there's a lot of investments going on in terms of how things are moving forward. And the kind of course, the environment that is being built is also quite unique as far as I'm concerned. And this is one of the reasons that I moved there and started to build 3 research centers, one on AI, the other on telecom, and the third one on cybersecurity at the moment. And the kind of vision that we have is, of course, to attract the best scientific minds, because that's the only way that you can basically, of course, create a bit of a strong ecosystem. Then, of course, work on very challenging problems. And there, of course, there are many challenging problems, especially with everything which is related to climate change and how technology can change that. And of course, become a world leading institute in terms of what we're doing. And I told you the kind of similar idea we have in terms of what kind of things. We're fully funded, by the way, by the UAE government. So although we're a private entity, but we all fully depend on the UAE government. Okay, so my talk is going to be about 3 steps. And depending on the time, I'm going to insist more on one. The first one is a more general introduction on the topic. Second is a new discipline, which is rising at the moment quite heavily in the telecommunication field, more on the fundamentals, called Electromagnetic Information Theory. So talking to people like you, this is something maybe you're a bit familiar, although you'll understand why we're talking about the unification of something that people have been trying to do for many years, called the unification of electromagnetic theory and information theory. And so you've been seeing it maybe in a couple of journals, like Antennas and Propagation, IEEE Antennas and Propagation, and also in information theory, which people have been doing. And the last one, which is starting to come heavily, especially in one of the key KPIs of 6G, which is called mobile broadband, meaning having more rate, is the fact that we're trying to exploit more and more what we call massive modes instead of massive MIMO, which is basically, and we'll try and understand what kind of things this can bring. And I think you've been all hearing about Vortex, OEM, things like that, and announcements which have been done recently on the kind of capability and rates that we're going into. And for which, of course, also the work that you're doing here today related to everything, which are these new types of antennas that are being built, are part of that. Because as you know, depending on the kind of antenna that you build and what we call the boundary conditions, you can create new types of modes that you can exploit. And if you do it intelligently, then you can transmit, depending on the situation, if you're line of sight or no line of sight, on how you want to do things. So momentum. So these kind of articles just date back quite recently, 10 February 2022. You see February 14, 2022. The word 6G comes in, and also the word radio waves come in, Vortex come in, with a huge announcement of the kind of data rate that we've been able to achieve quite recently last month. And especially the kind of data rate that we're trying to discuss about is basically things which are of 1 terabit of data per second, which is basically a huge target, as you know, and this has been achieved. And this has been achieved with what people talk, it's about introducing a new physical dimension. So I think this is something for you would be obvious, we'll talk about it. But in our discipline in telecommunication, this is not something we're quite used to, because we have a very difficult understanding of electromagnetics. And the fact that we have a very difficult understanding of electromagnetics is that usually we take what we call statistical models to represent everything. And today we're able to go deep in those type of equations because of the computational power we have. And that computational power changes everything, because we're able to crack down all those equations and solve them in a very precise manner. We're able to embed our information on those modes of transmission. And then, of course, we need to demultiplex those modes. And this is what I'm going to talk today. So what I mean by that is that there's a big trend today. China, of course, is leading the race at the moment. But a lot of big companies, big research centers are going towards that track in terms of moving forward, because one of the targets, we'll talk about it, is how you can achieve 1 terabit wireless, which is extremely difficult, as you all know. So I think you're quite familiar with the generations, which is going on. Today, we're really roughly here. The generations are basically 2G, 3G, 4G, 5G, and now everybody's investing today on 6G, okay, which are basically generation of a 10-year time frame. 10-year time frame means basically that every 10 years we change of generation. So generation needs to be different from what we call a technology. For example, in 2G, the KPI of 2G was mobile for voice. However, there's various technologies that can solve this KPI. You have to distinguish, and GSM is one, but you have IS-95 and many others, okay? 2000, 3G was mostly about mobile for data, okay? Same thing, there's many CDMA 2000, TDD CDMA, which fulfill those requirements, for example, okay? In general, by the way, the generation is 20 years. Okay, so it doesn't end from 2000, 2G did not end. Usually that lasts 20 years, even more in some cases. Now we're shutting down, I think you read the newspapers, a lot of 2G and 3G networks are shut down at the moment because of this reuse of frequency. 2010, mobile for internet, same thing. That's the KPI, many things behind. WiMAX is a 4G technology. LTE is a 4G technology. So you need to distinguish what we call generation from the technology that will fulfill those KPIs. Then, of course, there are some technologies which are more successful than others, but this is in general just the business out of it. But when we fix the KPIs, there's many technologies that can fulfill those KPIs. Here, I'm roughly giving you what's the general trend of that generation. Of course, if you go on the specification, you have very specific KPIs, which are related to what is mobile for voice, for example, and for which you have room, you have handovers, everything is well precise and explaining what you can do. Clear? 5G came in with one of the main requirements, which is mobile for things and all the explosion of what you would call here the IoT. Okay, that's the main target. Although today you have to know for some reason, the big market of 5G is mostly around what we call the MBB scenario. We're mostly using the mobile broadband today, and that's what's massively deployed today, rather than looking at what we call here the massive connectivity, which is starting to kick in with all this industry 4.0 that we're talking about. By the way, just an anecdote, we were so focused, for example, in 2G, and this is for in 4G, in mobile for internet, that you have to know that in 4G networks, voice does not work very well. Because in 4G, it's a voice over IP system. It's internet. Clear? And so you have to know that was a big issue in which I worked many years, because basically we had to develop something called voice over LTE, which is very specific. And when we sold the first phones on a 4G network, people were complaining a lot. And why they complain? Because you sell them a phone and they say, I can make a better call on a 2G network than a 4G. It doesn't make sense. But we tell them, no, but a 4G is to browse. And we made during many years a switching system where you would browse on internet on a 4G network. And when you make a call, you have what we call a CS fallback, circuit switch fallback, where you fall back on 2G, 3G to make your call. And many, of course, also of the deployments that we have still have this thing, by the way. Okay, but now voice over LTE has been improved. It was very difficult. We used AI techniques to do that. Okay, because it's an end-to-end metric. I mean, you can't improve voice over LTE by doing better coverage. Whatever, even if you have a super SNR, it will not change because it's all about the protocol, which is behind IPsec, where the servers are, things like that. So it was extremely hard. And AI was extremely nice to work in because in general, it's this black box approach where you don't have a full understanding of the whole. And so you represent the whole thing as a black box, and then you run your machine learning algorithms, okay? And then the things that now is starting is basically we have a very good clue that AI is going to be everywhere. We're going to have a lot of devices on which we have intelligence embedded. And we're looking at something which is related for mobile for intelligence, how you connect intelligence. Because we know that around 2030, 2035, there will be more and more AI entities, and for which we're building a super distributed computer which connects a lot, and for which the speed at which things have to be done, the latency at which have been done, the kind of communication which transits is not about humans talking to humans, humans talking to machines, but machines talking to machines with intelligence. Okay, meaning that they have, and for which you're starting to see, by the way, a lot of work of pushing back the cloud AI perspective towards what we call edge AI. I think you've been seeing edge AI terms everywhere, where a lot of things are happening now, everything on the AI on the edge. We're running chipsets, which are called neural processing units, and in which we need to connect on how you communicate between one neural processing unit and another neural processing unit, which is quite far, okay? Now, of course, that's the general trend. Then, of course, 6G has been, in fact, moving more forward and looking at much more things which are more precise, which are basically the extremely immersive experience. The fact that haptic is extremely important today. Sensing and imaging, because you're building intelligent machines, have to go around, which is also another venue in terms of how we're doing things, because communication was mostly about sending bits, but today everybody realized, and this is why I think you're targeting a very good market today, is we're using wave to do something else because we're talking about machines which have to move around their surrounding. So they need to be like a seed environment at different frequencies, classify, learn, and stuff like that. So this is becoming a big hype, a lot of investments. And you can see it also from the stock market of LiDAR companies already now rising high. And this is also going to get more and more. Industry 4.0 with connected intelligence that I talk, the smart urban knife. Another thing also, which is extremely hard for us, is 3D coverage. Okay, and for which we still don't have an idea on how to do things, meaning that we have a terrestrial infrastructure, we have satellite infrastructure, how we do basically the connection between both, or should we not? Should we only use terrestrial? Should we use moving base station, what we call flying base stations? There's many scenarios trying to provide that. So when we're talking about 3D coverage, it's very simple. It's not about, super intelligence. It's just about having terminals which move in the air and for which you need to provide data. Okay, so typically it's a helicopter going from Charles de Gaulle to basically La Défense, which is a various thing. But we know that this is going to happen by 2025, and you're going to have things which are going to be very easy to do every 20 minutes. And for which people, when they go in, they want to do internet, they want to make calls, and for which you need to provide 3D coverage, for example. Okay, the native AI, which is at the heart of all the network, for which we have a computing infrastructure, okay, which not only communicates, but computes also. This is also a very big changer. And for you guys also, it's very important because within what you're doing, we're also seeing metamaterials, which are not anymore just doing some kind of processing and transmission, but they're also computing. And you see a lot of work being done on that discipline, okay? And that the reason is, of course, because this kind of computing capability is going to be nearly at any point in the network, okay? And for which, of course, we have a lot of applications around that. And the last one, which we did not sell for 5G, and I think you saw burning base stations today and everywhere, is the thing here, which has become extremely important for us, okay? Meaning a drastic reduction of the consumption of basically the network that we're building because, of course, of all the problematics that we have, and for which we don't have a solution up to optimization techniques. So, of course, breakthrough in physics could be the way to go. And we're looking for breakthroughs in physics to be able to solve, because the only way we have today is on-off techniques, sleeping mode of base stations, sleeping modes of small cells, sleeping modes of antennas, doing what kind of optimization by running different algorithms. But we don't have any breakthroughs in the physics on how you do. And of course, the trend of having a much more number of antennas in our system has put this thing as a red flag, okay, in terms of consumption. And it's not something that you should only think as a point of related to saving the planet. It costs a lot. So if you take, for example, an operator like China Mobile, we're talking about network in terms of energy bill, the whole network, not just the wireless part, not only the radio access network, 4 billion per year. So if you do 50%, which is, okay, 10%, let's do it 10%. But you go to 50%, that's $2 billion of savings. It's huge. Okay, so it's also a lot of money. And as you know, energy is not going down, especially these last 2 weeks. the bill is only rising in terms of just maintaining a network like that. So this has become extremely hard for us, and we have no clue how to solve it. Okay. Now, of course, in the trend that we're going to talk about the future, we're here with 3 things that has been designed and for which we have the solutions, but for which today the operators are mostly concentrate on this. Okay, EMBB meaning providing more data rate. MMTC providing connectivity to all the objects that you have. We're talking about 1 million objects per kilometer square. Ultra reliable, low latency communication, meaning reducing drastically the latency in terms of how you communicate, car, automotive car, things like that, and extremely reliable, which is a problem in communication because your reliability on a phone is okay, but when you're talking about critical infrastructure, it gets hard. But these things have been already done. But the operators have mostly deploying this, and this is going to come by next year, mostly. Okay, and the main reason is that we know how to make money out of this. We still don't know how to make money out of this. How do you sell basically reliability and make money of reliability or latency? So we need to think about it, and people are thinking. However, we're seeing already a progress towards by 2025 what we call 5.5G. And for which the 3 points have become more like something hexagon. The first one is uplink-centric broadband communication. What it means that the kind of devices that we had, which we thought were sending tweets, Twitter-like, very small data, now they're sending a lot of data, and it's massively. And the uplink is a bottleneck. So why is uplink the bottleneck? Because usually the device has very low energy. So it's not like a base station. And second, you cannot embed MIMO systems in it, multiple antennas, okay? And of course, the target is the huge number of cameras that we're deploying. There's a massive number now. This is, of course, connected machine type communication, and the number is huge. It's not only about cameras which are deployed in cities, things like that, but also the number of cars have up to 8 cameras on which we want to have live streaming of all the information. Those cameras are not used for basically avoiding accidents. We have now a lot of car makers which are using all the cameras to build platforms of the Google View type. You know what I mean? So you have an online information about everything which is happening in the city, and you want to look at what happened at 5:30 outside the thing, you can see. And you can imagine, you can give it even one more step. You could, in 2045, look at what happened in Paris for historical reason in 2021 in that street. That information will be there. So we would be able to gather all reconstruction of our environment. And I mean, if you could see in a classroom with your kids what happened during the battlefield of Napoleon, you would be extremely happy. Okay, imagine. So you go back to history and say, okay, let's go and see how the battle went in, and all the cameras were filming, and we can stock that information. So you can see the kind of moving platforms that we're doing, and this is going on because basically we have now the information, we can bring it back, but we have a bottleneck, which is the uplink, which we don't know how to solve. A lot of people are not working on the uplink centric. Clear? Second thing also, which is coming on, is the combination of what we call real-time broadband communication. So in general, there's a bit of contradiction in communication between having a high data rate and reliability. Reliability means redundancy. Okay, if you want to be reliable, you send 2 times the packet, two frequencies, 2 different times, 2 antennas. So in general, you reduce your rate because you're adding redundancy. So having at the same time high data rate and real time with reliability is extremely complicated. And so this is something also that we're working on, and a lot of applications related to holographic MIMO, XR Pro, which is what we call RTBC. And the last one, of course, which has already kickstarted and for which the market will kick in a lot in 6G, is of course all the things which are related to communication and sensing, which is already happening for 2025, and for which we have already solutions for that. Clear? So this is already a milestone for which we need to build stuff, and for which many people are working, and the standardization process is already trying to define at the moment with the solution which is coming in. Now, related to our target, which is 2030, there's been already consensus today on basically what we call IMT 2030. So IMT 2030 is the engineering term of 6G. Okay, just like IMT 2020 is the engineering term of 5G. Okay, so because usually 6G is just a marketing term, just like 5G. I mean, if you go into detail in your industry, you'll see that many people will talk about 4G and 5G without being a new technology. They will mix things which are just because they achieve a certain rate. Okay, so these are basically got a consensus. It's not self-finished, but already nearly all the companies, all the community is agreeing on the targets. And you can see one of the targets is a peak rate of 1 terabit. This is why I started with this big concentration of having this terabit wireless. A network capacity 1,000 times with respect to 2020. An air interface jitter, which is very reduced. Something which is in the communication and sensing part that I talked, which is positioning. So positioning is a very hot topic today, okay? Especially indoor positioning, for which we have no solution today on how to do accurate indoor positioning up to, as you can see, 1 centimeter indoor, okay, in non-line of sight scenario. Extremely complicated because we're talking, you remember, about mobile for machines that need to move in front of their environment, so they need to know exactly how to move around. Then you have an air interface latency, reliability, which has also increased. And then you have also the rest, which is related to energy efficiency and guaranteed rate. By the way, you need to always differentiate, because people tell me, oh, I have a subscription about 5G. They told me 10 gigabit. I don't have 10 gigabit. 10 gigabit is the peak rate. You'll never get it. Okay. Okay. And even in the best conditions, you'll not get it. Why? I give you a very example. 10 gigabit to get it. Basically, in the definition, you would need basically around 400 megahertz of bandwidth. Okay, which means that basically, if I take in France where it's deployed in the 3438 gigahertz band. It's called the C band. Here, there's 4 megahertz, but it really depends on the countries. In France, we made a choice of having 4 operators. So by definition, already when you start, it means that any operator will never have 400 megahertz. At best, you'll get 100 megahertz. So already you have a hit. And then once you do that, then there's also the configuration that the operator decides to deploy for that in terms of antennas, things like that. And so this is why you will have very different, what we call quality of experiences, depending on the countries where you are, because it depends on how much bandwidth the operator was able to buy. Clear? However, in the specification, if you do all the fulfillment of getting 400, blah, 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 you would get the 10 gigabits per second. Clear? So this is why the experience of 5G or 4G that you would get will be different in many different parts of the world, but also with different operators, because they will not decide to take all the different, I would say, peak things that they were asked to deploy. Okay, and then it's the peak rate. What it means also it's divided, and so depending on the cell where you are, it goes drastically. So typically, for example, 4G, if you look at the specification, it's roughly around basically 1 gigabit per second peak rate. But if you go out, you get 30 megabits. That's exactly what you experience. 30, 40, you can go to 50. Clear? So yeah, I think it's very important to make the differences between that. Same thing when you compare energy efficiency. There's no one way people are saying, oh, 5G consumes more than 4G. Or 5G or thing. It's hard to compare. This is where all the discussions are going on, because there's not one single 4G. The 4G that Bouygues Telecom has deployed is totally different from what another operator, because depending on the number of antennas that they have deployed, their infrastructure, the choices that they made, they would have different figures in terms of consumption. Clear? So in general, it's very difficult to say this consumes much more than this. We have global figures, but it's operator dependent on how they decided to deploy, which choices they made in terms of bands. This is extremely important. Okay, some choices on the bands that you make can have drastic implication in terms of how you have a rate or consumption and stuff like that. But this is known. It's called radio planning. You have a lot of engineers in companies. That's why they work in operators, is to find basically the best parameters to do that. Okay, now let's go back. And my introduction was long. Let's go back to of course the timeline. The timeline is set. Okay, which is in general also very bad from my point of view when you do the timeline. Why? Because the timeline in general is set such as in 2030 we get basically the technology. But then if you do what we call retro basically planning, it gets bad, because it means that there's a consortium which is standardization. The generation is called 3GPP, by the way. We don't call it 5GPP, 4GPP, 6GPP. We kept the same name. It's the third generation partnership. It started with 3G, but we kept it. But they continue doing all the generation, okay? But as you can see, it means that the technology research, the core, has to finish around 2023, 2024. It doesn't leave us much time. It just means it leaves us 2 years to invent disruptive stuff. Because then there's a whole machine which starts. What is this machine? We have what we call in the standardization study groups. These study groups study all the technologies that are here. They start making some decisions in terms of what are the parameters, and this takes roughly 2 years with many partners which are implicated. The guys who provide the network, the guy who provides the device, the operators which are going to buy the stuff, on which there's a lot of discussion. And then you have a part which is related to specification when it is done. And then we start making the deployments and testing, which takes time. So as you can see, it takes overall from here around 5 to 6 years before we get the true deployment. And so in general, the key interesting time for researchers is roughly here. And you have to know that a lot of 6G research, I was at Huawei, but other places started already here. Same thing for 7G. It will start around 2028. People will start kicking in to prepare the future, because it takes a bit of time to go in. In parallel, however, it's an industry which is not so easy, because in parallel, you have also the guys who are doing 5G who improve the system. So the guys who are working here have always to look on the side and make sure that what the guys are improving, they have at least a number which is quite high to justify the fact that you'll change the infrastructure to make it happen. For example, you invented lease. Lease is going to be deployed. You could deploy lease in 5G. Lease, okay. We call lease, smart. So you could deploy lease in 5G. But then what these guys are going to do is they're going to start thinking, what should, and we have some performance of your lease, which is happening with 5G. Okay. But then what the guys here are going to do is they're going to start thinking, what should we change in the protocols, in the waveform, in the physical layer, such as we can improve more than the performance that we have. Clear? Just like massive MIMO. You could deploy massive MIMO in 4G. But then we took the deployment of massive MIMO in 4G, and when we deployed it, the LTE frame structure, the downlink, uplink, signaling, the frame structure made it that we could not have more than 32 antennas dual polarized. That's the maximum you can do because you cannot estimate the different channels on which you can change. So we had to tweak and build up something called NR, the new radio, to be able to move up again the number of antennas that we could build in the system. For RIS, or at least this is what will happen also. Once we'll start, testing it, we'll understand that OFDM maybe is not the best thing suited for RIS. I have no clue. Same thing, the kind of signaling structure between the device there and where it goes, the time, the kind of delay that happens, things like that are not fitted for optimizing the optimum capacity that you could do. Of course, in simulations you can do, but once you start doing with the frame structure, there's many, many constraints that you have which cannot enable you to kick the performance in terms of coverage of getting the numbers that you would get in MATLAB in the way it's done. So we need to take in all the technology that we're pouring here, some will be used here because the guy who invent here in general, these guys watch you and say, oh, you did the super algorithm, why can't I use it? They use it. And then they have a performance, and these guys will think, oh, they used it, why it was limited? It was limited because of this thing. And then we try to change. And this is why we build a standard, because then we create a whole frame structure, downlink, uplink, 10 milliseconds, then 10 milliseconds your talk, blah, blah, blah. We do it that way, stuff like that. Is that clear? And of course, all this is done with something very important, which in general is a bit difficult, is what we call the World Radio Congress. So every 4 years, all the community gathers. And then, of course, telecom guys fight with satellite guys, with military guys, because we invent something and we think that the best use case is in a certain band. And we have no idea if that band is available and in which country it's available. And the whole here discussions is about fighting to make sure that it's a worldwide band. Because again, if you build something for a band which is available only in France, your market becomes very small. Clear? And then you have to be sure that all the other countries, so there should be a harmonization. By the way, I don't have time to talk, but already in 5G, you'll see that there's not in a millimeter wave, for example, a harmonized band. You have many countries. C-band is roughly harmonized. In general, it's quite okay. Many countries have used the C-band, but millimeter wave, you have many countries which have made different choices because of the interference it incurs with the satellite military they have. Okay, so we have to work hard on these things, which are extremely important milestones. Okay, now let's go on the research front. Oh God, yes, I'll go fast after, but I have a bit more time. Okay, but I think it was important for you to understand better. Now, what are the degrees of freedom that we have today to make things better for the future? Okay, so I took time to read all the papers, look for you. What are the big hype directions which are mentioned? There's 4 big things today in which people think that we can make some breakthrough to move forward stuff with respect to what happened in 5G. The first one is, of course, the fact that we have now in our communication a lot of memory, capability of storing data at every point in the network, and which makes it that basically we can build up new types of communication which are smarter in how you transmit data. Give you an example. If you take, for example, the way Shannon built up his model, you have a transmitter receiver, okay? You transmit your data, okay? But then next time you transmit the data to the same person, clear? It's a new communication scheme that you do every time. There's no context which has been built within your communication because the data has not been stored, okay? We know as humans, the more you communicate, the less you need to communicate after to the same person because you've built up some kind of contextual. You can compress. There's less information you need to send. There's things which have been contextual. This is called semantic communication. And this is a big thing which is happening today because thanks to AI, we don't need to store. We just need to create the model out of the data. The model of which I've been communicating with Geoffroy, the model which I communicate with Matthias, because basically the more I talk with Matthias, the more there's some kind of common understanding which happens. And for which at one moment, there's less things to transmit, okay? Whereas in the Shannon point of view, every communication is a new story. Even if I communicate with my mother every day, the way it's built, because memory is not included in the system, okay? And today, memory is key. We have it everywhere. It's cheap. And we're embedding a lot of storage and, of course, computing behind, which generates information when it's called what we call common, basically, or context. Second, of course, which is extremely good for you, is that our engineers have been working only on the TX and RX all their life. That's it, because environment we cannot control. So we knew it, and I think you all knew it when you were in university. When the communication was not good, you put a fan and try to things to see if it goes. You move a chair, things like that. So we knew, of course, if you could move things, it gets better. But the problem is, can you do this in an automatic manner? Okay, in an electronic manner, which does not require things. And of course, many of you have been working on this. The fact that now the environment is controllable, we can change the environment. It's in the loop of our communication, has made drastic changes in how you communicate. And the question is, of course, for a given environment, how much you can pour in more is all still the key question. Okay, we have the fundamental limit in terms of Tx and Rx, no problem for a given environment. But now, if the environment is structured in a certain way, how far you can still push that environment to improve the whole system is still a key question. Okay, because of all the things that you can embed easily in your environment. And in the future, maybe move down the building, make the texture of the building so nice that the building is out. It doesn't appear. Exactly. So basically, how much you can go far to convert whatever kind of environment into an ellipsoid, so that you're the center and center by changing all the parameters is something. So this is heavily at the moment, of course, pushed on at the moment. Standardization has not kicked in, but all the researchers are developing different keys. The big problem with that, to be honest with you, is the same scenario that we had as a technology called small cells more than 20 years ago, on which I worked. What I mean by that is that the technology will be a success. I have 100% confidence. The problem is then when you look at the numbers in terms of deployment, because deployment is key. Okay, for the small cell scenario in which I worked many years, the big issue is that small cells improve the coverage, it's great. But then when we decide to deploy, we needed to power. We needed to find places where to put in. We needed to negotiate with the city stakeholder, and negotiating with city stakeholder is the worst thing that can happen for you. Today, for example, in Paris, putting a base station somewhere takes you 2 years because you need to negotiate with the syndic, ask the possibility to put the antenna. And then, of course, the guy who has the last floor in general is not happy. The guy on the first floor is more happy. And then there's a price, roughly 200K, because and that pays, of course, the lift and stuff like that. So it takes a bit of a discipline to do that. So they hate this job. So you need to find a way that you don't need to talk to many people. The best is that you deploy and you talk only to the operator, and that's it. Okay. But however, technology-wise, we see the benefit. The question is it going to be something else? Second thing I think also, which is important for you guys who are working, is the work that has to be done, which can take a lot of time in standardization related to what we call coexistence and interference. You have to know that people hate this also. So you can have one RIS, good for you. But imagine once you deploy many RIS, how you coordinate those RIS. You improve this communication, but on the other side, you killed somebody else. We had the same problem in small cells. Sorry for the same thing. Small cells were improving things when they were totally all coordinated, which was extremely difficult because we needed a backhaul to coordinate everything, a centralized scheduler to do all these things. Then we believed in a solution called SUN, self-organized network. We said, oh, we're going to put intelligence and it's going to be self-organized. The small cell will find its own parameters to do. It's like Wi-Fi. Imagine you have so many Wi-Fis and then you need to, more Wi-Fi is going to destroy your communication because they start interfering in bands. Then you say, I'm going to do some smart algorithm where this Wi-Fi will choose basically the best band depending on how far it's distant from the other. So you need to start thinking of all these things. For information, it never worked because of the fact that you're mobile. So what it means that when you do distributed algorithms, they need to converge very fast because by the time you find what's the right optimal parameter, there's a new layout. You know what I mean? Users have gone out, they get in, things like that. So things have to go at an extreme speed, which turns out algorithmically to be very interesting, but basically complicated. Third one, which I want to also stress on, is the fact that we also realized that we have a lot of discrepancies with your antennas, for example. There's many problems for power amplifier, especially when you go in regimes of millimeter wave. And even in OFDM, we have something called PAPR, peak to average power ratio. All these things, for many years, we were trying to compensate to go back in what we call the linear regime. We hate nonlinear regimes. We hate them, okay? And so we realized today that doing that costs you a lot. whenever you compensate, you do back off in terms of power, in terms of the whole system, you lose a lot. And of course, there's been some breakthroughs. I don't have time to talk about it in understanding how you do nonlinear transmissions or transmissions in nonlinear systems. Okay, and for which you can find, instead of saying, oh, Fourier is basically some kind of eigenfunction of your linear system, we have now nonlinear Fourier transform for specific, for example, type of systems. Just like you would say, what is for a given environment which is nonlinear, the best kind of eigenfunction I can find? We've been making some breakthroughs. And second, when we don't know the kind of environment we have, AI has helped a lot. Because we know now how to embed basically systems which are nonlinear by learning, but then we don't have, as you like guys, an explicit mathematical formula for that, but we have a constructive way, numerical waveform, which is optimum for that kind of environment. So if you give me a power amplifier today, which is nonlinear, I can find you on an end-to-end AI system what is basically the way to input.
The nonlinearity you are speaking is on the electrical components, or is it in the wave propagation?
No, component, but of course with your lease, this can happen. If you start doing lease and you have all the system, the whole system cannot be linear anymore, okay? Because depending on the kind of non-linearities that you embed in your system. But already for us, we used to be linear on the EM part, but then the problem when you communicate, there's antennas, power amplifiers, and all this is not linear, okay? And so what we did is smart is all the antenna structure, we learned it and made a back off or made an inverse function in the Fourier domain to compensate it. I don't know if you understand. We're just trying to compensate the whole nonlinearities. This is huge cost.
Yeah, it's much more complicated. If it is not nonlinear, it's difficult to use the concept of inverse, but it can be done.
Yeah, of course. So what we say is, in general, we say we have the TX bar which saturates, and we try to just compensate. So we go in the linear regime, you say, or compensate by doing some inverse on some parts, yes. But today we use a lot of AI techniques where we represent this by a black box, and we don't care what kind of medium when we learn it. But of course, then I mean, I don't have time to spend time. We have a learning system which is basically time variant. So of course, there's many issues. I mean, it changes over time. And the last one, which is also good for you, is of course all these things where now, thanks to the computing power, we're exploiting new physics phenomena. Okay, which basically we know that these are good to do. Okay, I don't have time to go on this. You have to know also on the computing part. There's also been some breakthroughs that now we're using around that. Okay, let's go on the electromagnetic information theory, although the time has been gone. So the fact that people have been willing to merge two disciplines is not new. You have many people who have done it in the past, okay? And the question is, why do you want to do electromagnetic information theory? You have people that have done when Shannon meets Wiener. So you ask me, why would you do when Shannon meets Maxwell? Huh? Because that's what I'm trying to do here, okay? But you have to know, in general, people like this. Shannon meets Nyquist, Shannon meets Turing, Shannon meets Carnot. So the number of papers where one guy meets another one. And in general, of course, the idea of all these people is to, let's say, see the whole discipline in a new point of view, okay? So you see how, with this point of view, I can reinterpret. My question, of course, is that, of course, if you tell to the industry, I found a way to reinterpreting your equation, he says, I don't care. Because I mean, what I care is performance. Okay, it's good for you mathematically. You have a new way of explaining it, but it doesn't matter. Okay, what I mean by that is that all the people who have worked here, it's not necessarily about just reinterpreting. In fact, when you start merging two disciplines and having a different look, you can also improve the system. And one thing, okay, I don't have time to talk about it, and I worked. Talked about it is, of course, something that helped a lot in basically working on something called not the water filling formula, but the mercury water filling formula, for which I worked a couple of years. So we had a big problem. Basically, you have to know, in general, in communication, there's a nice paper of Shannon called Communication in the Presence of Noise that tells you, okay, whenever you propagate your information, your channel is bad like this. So it has good parts, it has bad parts, it has bad parts, good parts. Okay, so you're communicating over a channel. The theory tells you what you're going to do to transmit over a channel like this is you're going to slice it. You're going to put it in an extremely slices, narrow slice. The narrower it is, the better it is. Okay? Which is basically at the heart of proving that OFDM is optimal. So if you know the channel of the transmitter, you have to know that you cannot do better than OFDM, because you slice your system into very narrow bands. And on each band, what you do, you find what is the best way to transmit. And the best way to transmit tells you that this is called the water filling formula, which is used in ADSL. Whenever the channel is good, you transmit like hell. Whenever the channel is bad, you do nothing. Because compensating is the worst thing you can do. It costs you a lot of energy to compensate. If your goal is to maximize the total welfare or the capacity. Now, if you're looking at something social, you can spend time on losers. But meaning if I have things, I will only look at the best and they will push, and this is the way it's done. So this is called the water filling formula. And the whole philosophy is that you calculate the capacity and you have what we call the power and bit loading. You can find what is the number of bits and the power that you put in each one. Clear? Now, in our community, it's extremely known. Okay, in ADSL, it's called DMT, discrete multitone, for information. In wireless, that was one of the breakthroughs that we did in 4G, in looking at the different users and knowing he's good, I send him. He's bad, I don't send. Okay, but not sending does not mean that you'll never send him. You have something called a scheduler in our system, meaning that we delay. Okay, and of course, the system works well for 4G because basically data in general is okay with being a bit tolerant to delays. Okay, you're very bursty in the way you transmit. We transmit a big packet and then you view it, and then we have time to serve other users and do it. So we only serve people who are in extremely good conditions. This is why your system always works in the peak. We never waste time on people who are not good. Okay, so we prefer cutting the connection of somebody which is bad rather than trying to send more power. It's like a wall, you know. You can transmit and you pumped all your energy, you don't have any more energy. However, the formula that tells you this is based on a capacity formula, meaning if you decide to transmit with what we call Gaussian signaling. I don't have time to talk about it, but in general, when you transmit QPSK, BPSK, which are constellations. And so solving this problem turned out to be extremely difficult for many years because we don't know how to water fill when you tell me that it's your QPSK that you transmit and not Gaussian signaling, which is the capacity. Okay, but just to tell you, so we were able to do it by going on the signal processing front using Wiener's approach. And by doing Wiener's approach, just to tell you, when we did the merger, we were able to build up something called the mercury water filling formula, which in fact proves you a lot of gains that you can do. But just to tell you here that reconsidering a problem in general tells you, of course, new solutions to the problem that you cannot solve. So in general, that's good. Now, of course, making Shannon meets Maxwell is also not new. So many papers. So here, capacity scaling of wireless networks, Shannon meets Maxwell, which year 2012, as you can see, information theory and electromagnetic, are they related with Loika? So there's been many papers which have started. And so here my discussion is about, of course, this chart, which never finished, and how now it's becoming more and more important. So of course, I think you're all familiar with the famous paper of Shannon, and the paper of Shannon was unfortunately called a mathematical theory of communication. Okay, and it was all based about statistical approaches of solving the problem of communication by even representing the channel as a statistical feature, Rayleigh fading, whatever you can consider. It's statistics. And of course, all the guys like me who are good in mathematics love this because it's statistics, and then you play with statistics. Of course, a couple of years later, a guy I think you know very well, Gabor, came up with another paper called Communication Theory and Physics. And when he explained that there's a problem, we're not taking the physics enough in our system, in how we're pushing, okay? And you can read it, he says, communication theory should be considered as a branch of physics and not a branch of mathematics. So there's always been a fight between the guys who are more coming tight. And here, of course, is to bridge the two communities and see how we can solve these things, okay? Now, when we're talking about basically this electromagnetic information theory is talking about the whole thing, looking at this part, which is something we master in information theory, something we master in information theory, and for which we never wanted to take part of talking about what happens here with the antennas and this part here. And as I told you, because it's so difficult, it's ugly for us. If we go into these equations, it gets ugly, and I cannot even represent how I can transmit information, okay? And of course, today, the computing power that we have enables you to do that. So of course, here, the idea is that the traditional models of course, that we have in general, which are always far field, by the way. We always use the far field approximation. This is something because we know how to solve those equations that you have. Turns out, but today, because of the frequency we're using, because of the antennas that we're using, all this falls down. And now we're seeing new things that we don't really understand and for which we need to have an impact. Of course, as of today, there's a big trend related to this modes and things which is called holographic communication. It's becoming hot, for which there's different interpretation, and we can spend time also at the end on these different interpretation of holographic MIMO. Now, of course, why we don't use these things is that, as I think this is your community, you're quite familiar, of course, with what we call basically the circuit theory, transmission line theory, surface EM theory, and general EM theory to represent basically the different things of antennas. And of course, some kind of adaptation of independence and some kind, of course, of representation of the whole system with the conductance or resistance, things like that, in terms of making your life simple. In our community, we don't like it because this is how it looks like. Okay. And writing a system in which I can tell you the capacity of this thing turns out to be horrible. I don't know how to do it. And I think you're quite familiar when you try to solve the thing. And of course, depending on the boundary conditions that you have with your system, things like that, it gets ugly. Of course, it gets ugly, but today with I told you the computing power, things are changing, okay? Meaning that we can run routines to be able to get it. And so of course, the people, instead of doing that, have been using the classical approaches of far field to do that. But just to give you an approach that it's wrong what we're doing, and we learned a lot thanks to you. So for example, the capacity system, so you have here an array of antenna, okay? And you have another array of antenna, which is on the other side, on which you want to transmit, okay? Now, if you have a system in line of sight, in the classical MIMO setting, the numbers of degrees of freedom that you have when you take the far field approximation is a degree in 1. Meaning I cannot multiplex data. Okay? And we thought this was true. This is why we started digging in what you're doing to understand better. And why? Because you have what we call full array gain on RNS. And what I'm saying is that, of course, I'm taking functions which are of this type here. And if you write them, you can show that your matrix, which represents the rank is 1. The rank of that matrix is 1. But because of that assumption that I'm making, which is of this form of type in terms of how I embed my information in terms of how it's transmitted. Clear? And then if you look at the capacity, which is usually called the log determinant, I don't have time, you have only an energy gain. You have to do that in communication. We hate energy. We like multiplexing. It's what we call the pre-log factor. It's the number of multiplexing that you could do. So MIMO was great for us because it increased the pre-log factor. The more antennas I use, I can have more pre-log factor as long as in my environment scales with the rank of my antennas. If I have a rank 1, if I put 1,000 antennas and at the end I still have a rank 1, I have only a logarithmic scale of my system. It's an energy scaling, but not a multiplexing scale. Okay. Now, of course, if I look at the classical MIMO communication, okay, and if I take antennas basically which are of the type 0.2 meter, receiver is 2 meter and distance 10, and in which, of course, I start looking at the real stuff where I can compute spherical waves going on distance. We realized by doing our experiments, it's totally different. Instead of having a degree 1 of freedom, we have a degree which is related to LSLR divided by lambda t, meaning that we can pour more energy by exploding, basically, those different features of modes. So for you, it sounds, simple. But for us, it was a new revolution because we had for a long time saying that it's useless to put MIMO systems in line of sight. So if I see you and you see me, if I put 10 antennas, it doesn't bring anything except energy. But I cannot multiplex more. Clear? However, depending on the frequency that you use, as you can see, lambda, the size of your antenna, and this is changing. Of course, the assumptions we were making, because we didn't have computation power and using the classical basic assumption of far field, made it sense. But now things are changing completely. And so we have ways of multiplexing more data in a system, basically by using these things. Second thing also that we're seeing also with you guys, and I think you know this guy, I think, Nader, yeah? Is a very good friend of you, yeah? Is also, of course, that we can start also with antennas manipulating the waves and changing. So it's not only related to the electromagnetic by itself, but since our channel, when we call a channel, what we call a channel is not just the wireless. A channel for us is the end-to-end, by the way. Okay, the TX is the whole transfer function, which takes into account this. And now, of course, bringing in the new type of antennas that you're building changes also a lot the pictures for us. Okay, and of course, a couple of papers which are appearing in community. This is a 2020 paper called temporal aiming. And the idea, of course, is to be able to start by propagating and changing the index. You change the index, basically, and you can change exactly the beam in which direction it goes. So this is also extremely revolutionary for us because for us, the antenna was an antenna. And we would do some kind of weighting, which is electronic weighting. This is called beamforming with the digital weights, and for which we could change. But we didn't have any other degrees of freedom to even change and have an impact on the environment. And here, thanks to antenna, we impact by changing the index at a very fast rate. So of course, these are the kind of new stories which are happening also for us, which changes the understanding of we need to embed basically that part on which we need to have the full equations related to this temporal aiming, but also RIS or LIS, or whatever things, how you call it in your community, to be done. And of course, this part is also related to now, of course, also that the channel for which we used to model things in a very simplistic manner considers also the new trend of having also the fact that the kind of reflections and things which are happening here changes also the new type of models on which we can change, okay? And for which now, just for information, the notion of information theory needs to take into account that this is, and this is hard, it's not an independent entity from this. Clear? And so if it's not an independent entity, the notion of capacity changes also completely for us. Okay, because the notion of capacity suppose what we call the mutual information between X and Y. And this is not considered. Yeah.
When you speak of what Nader is working on,
yes,
you work with him on this time modulated refractive index.
Yes.
In fact, you can combine RIS, which is a spatial modulated shape,
the spatial temporal.
Maybe space-time.
Space-time.
The problem we have yet is that we cannot change the electrical impedance of the surface
at the speed of the communication.
We can do it, but there are very interesting things that I will have to discuss with the team, where if you change the refractive index in a time scale which is quite lower than the period,
yeah,
the incoming wave, if you do a space-time modulation, you can very efficient effect. The problem is that the reflected wave from the RIS that is changing its property, we change its frequency.
Okay.
Which is like,
because it's like as if you were moving, there's some kind of Doppler effect.
Exactly.
Yeah.
Doppler effect. And because of this shift of frequency, if you want to play in a transmit-receive configuration, you have to be careful because you will not receive the same frequency for the input signal at the output point. But we can.
Yeah, I think I'll go fast in 2 minutes. I know people are getting. Okay, just to let you know, so I'll move quite fast because I can talk a lot. Just to let you know that, of course, also things which are happening to the fact that we now can embed is all the notion of having antennas which are with LIS exactly embedded at the RF chain, which create basically MIMO systems in some sense with only one RF chain. This is called holographic MIMO. So either you have LIS at a given distance, either you have LIS very close to your antenna, in which you can manipulate the beam. Okay, and this is, of course, as you can see, a whole new trend of people working to build these things, and for which, of course, you have extremely good directivity. Because the whole notion here is to say, this is how it started in our community, at least for the people who do a holographic MIMO based on LIS. By the way, you have holographic MIMO based on photonics. This is ZT approach. If you have time, you can take a look at it. But the idea is to say that I have a given surface. And if I get to my given surface, many people ask their question, if I start having more and more antennas on it, how far can it go? This is how it started. Okay, and because we want to know the limit. And of course, you'll start having what we call a continuous array, classically, because you put so much. Continuous array nearly looks at what you would call a LIS that you would bring here, exactly, and for which you would go within one RF chain. And this started a lot of activity related to this. And you have big players who are now building these antennas with good properties in many cases for different scenarios. And again, this opens the door for all the things that we didn't know in communication, okay, which you know in antennas and propagation, which revolutionizes the way we communicate, okay, because basically we were not taking the antenna was something independent. It's the classical thing, you have just a cable, you put electricity and it emits, that's it. Either it's directive or not directive, and we stop it there and it's fine, and we take it per se. But now we're seeing with you guys a lot of new features that enables a whole change in the way we do, and with which basically it changes the model and change. And I think many of you are working on some parts of these things which have different features related to what they can achieve. Now you have to know that historically, the kind of electromagnetic information theory, many people have been going on, but these last years, there's been a big number of players going in. But it dates back, as I told you, with guys like Gabor. Then you have a guy called Frascischetti. Maybe you know him very well in your community. Then another guy who was very well known, also another guy called Frascischetti, called Wave Theory and his book. And then you have Joseph Nosek, and you have also Sarkar, who also published a couple of papers, and people have been trying to merge both. And of course, each one have been trying to look at different features to simplify our life, either by looking at a secret theory version to be able to do the whole thing. You have, of course, other people looking at different things with degrees of freedom of how much we can gain. Even the guys of Massive MIMO have been going on in looking at electromagnetic information and giving courses, by the way, on what I'm saying at the moment, in embedding both. He has in NYU a course, and it's going on. And now, of course, the question is, what can it do? What these approaches of adding the equations, understanding better the equations, the new modes on which you can do. Of course, basically, you have the fact that you can increase capacity, especially in line of sight. And this is a lot of work which is being looked at today at how you can orthogonalize your mode. Second, of course, you can reduce the complexity of your transmitter. So typically, if you want to do millimeter wave communication today with 8 gigahertz of bandwidth with the DSP, okay, it's extremely complicated. Okay, it's trying to not exploit the full classical MIMO matrix, but trying to exploit the modes, OAM, for example, with line of sight. If you can do, then demultiplexing is more easy. So the gain also of exploiting those modes is not a question of just improving, but it's reducing basically the processing to be able to get them. Okay, then of course you have also new types of channel models which are arriving, new types also of antennas, okay, which are also now embedded in the discipline, and of course also all the things which are related to wave control, okay, in terms of the consequences of going and digging more into these things. And of course today you have a couple of people who are trying to build up the whole thing around that, which are community working on holographic MIMO, on what we call extreme large array aperture, okay, it's called ELAA, okay. You have intelligent metasurfaces, or whatever, how you want to call it. All the guys working on OEM, which is also, by the way, the first thing that I showed at the beginning was OEM based, the 1 terabit, okay. Far field to near field and spherical wave. And of course, the kind of different things that it's opening doors in communication goes back to the lease that you know very well, the super directivity compact antenna design with sub-wavelet scale and things like that, the massive MIMO extreme large array aperture, and everything which is around OEM and spherical wave, which is happening around that. Now, let me just give you an example on which I've been working since now 2 or 3 years with a couple of colleagues, especially Luca Sanguinetti, looking at how basically based on the boundary conditions, we are able to exploit what we call wave number division multiplexing, basically in the wave number domain, okay? Which supposes, of course, some type of configuration, and for which basically you can do a system which is much better than the classical. But here what I'm talking is a more general trend of whenever you solve equations, on the equations you solve with the boundary conditions, you found modes. And the question is, how can I exploit them to transmit my information? And I tell you, it's not necessarily also of capacity, but also simplifying your receiver structure. Because today, if you have large bandwidth, doing DSP is extremely complicated. Okay, especially in the frequency band that I'm talking about, gigahertz. So of course, what you do, and this is your job, all of you. I think these are the kind of equation you love, with basically current. We're less classically related to that. We like the y equal s plus n and S is a signal, things like that. We don't need to go. But you're quite familiar with these things with the Greenwave function. Then basically what you do is that you expand your current in a given base, okay? The base has good properties so that correlation is maximized at the receiver. In our language, this is called a match filter, by the way. You filter it to maximize the output in terms of not reducing some kind of information. Then basically when you transmit, you have the classical basis on which you did, and these are the parameters that you would like to have some structure. So the idea in general of looking at the wave number domain, classically than the signal domain, is just to exploit better the structure of your matrix. And by exploiting the structure of your matrix at the receiver, you can demultiplex easier. Is that clear? Because if it's sparsity structure, so what we do now is that we look at the new channel in the wave number domain, in the mode domain, and if it has some sparsity approaches or some structure, we can exploit it to do better transmission. That's the whole idea behind. Okay, because if I take it without making any consideration and say, what I receive is a full matrix on my whole antennas and try to inverse this matrix real time, it's not possible because you need to inverse this huge matrix, which is a MIMO matrix, on each subband. So if you have 8 gigahertz a band, you cannot do real-time processing. So you need to start looking at, if I do a line of sight communication, there's structure. Because I know how the equations are. I can solve them. I can exploit that structure to embed my information, and then the receiver is much better, okay? And so, of course, when you do, that's what we did. And then you have a matrix. The matrix is more structure. And then basically what you're going to do is that you're going to look at the basis, which is usually called the Perot spherical wave functions, which you're going to do and try to exploit these kinds and look at an implementation. So, of course, the idea is exactly what I'm saying. You look at the basis on which you transmit with this line of sight assumption, and then you do some pre-processing and then post-processing that you can do. So you can do the pre-processing because the equations are known. So you know how to solve them. This was also a big question for us. So in general, in communication, we don't know how the exact equations are. By the way, this is only solvable in line of sight. Clear? Because that's how you can write your equation. When you're not line of sight, we hope also with the computational power that we have today, we'll be, I think I'll go fast. Okay. Huh? Yeah, I'm going to finish. Maybe, yeah, okay, good. And so this is what we call this wavelet division multiplexing. We've been considering different basically type of receiver with respect to optimal. And in fact, with transmitting on your mode, you're able to achieve something which is not far from the optimal system that you want to do. I have 2 other slides, but I'll finish. I won't go in. We worked. The community is also working now, of course, on building what we call circularized polarized OEM to be able to transmit on line of sight, because this is also a big issue. And you can show also that by building these OEM, I worked with my colleagues in Huawei on this, you can build up also some kind of transmission scheme which exploits basically the OEM structure that you have in your transmission. But I think I'll stop here. These are just examples on which I've been working since 2 years with many colleagues that I had on these things which exploit those things. I think I'll stop here and answer your questions. It's going to take more time. Okay, so I hope you got a bit of the idea of where the system is. Again, it doesn't mean that all the 6G people work on this. This is for the EMBB scenario of 6G, which is related to, if you remember, to the 1 terabyte. Okay, if you remember. There are other problems that we have which are related to that. And just to give you a hint is today for the EMBB scenario, this is exactly what our competitors are doing. To improve the rate, they're doing experiments in line of sight environment, pure line of sight things, and trying to exploit the modes to build up this 1 terabits to be able to do multiplex with extremely high bandwidth. Okay, bandwidths of 8 gigahertz, 10 gigahertz, 20 megahertz band, for which the DSP that we have today is not capable of processing that in a classical MIMO setting. Okay, just saying it's a MIMO matrix. Boom, 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 boom. I'll do a lot of processing of each matrix, and if you do it in an OFDM setting, you're dead because the number of subbands that you have is huge.
And what happens if they want to push this in complex, not in line of sight, but in complex media?
This is a good question. So the progress that
it's a question for us.
Yes,
in fact,
yes, it's not easy. So OEM, for example, does not work when you're not line of sight. You have to know. Okay.
Yeah.
Huh? Yes, what? Yeah, it doesn't work in line of sight.
Agree. Yeah,
But your question is important in the sense that we need to find, when you have reflections, things like that, how to solve it. The philosophy today of the people who are working in this discipline is to say, today we on a phone, we're able to build a supercomputing radar that can reconstruct the whole thing. So we could reconstruct online the whole equations that we have real time, and be able to find what is the best at each time way to transmit information by reconstructing the environment with the texture of the environment. I don't know if we can go this far, but I mean, imagine what you do in a Cyrano or whatever. Imagine that you could have everything and you could write the equations with all the boundary conditions and nuclear power on the phone. Okay, so you can do and do. How can you exploit that in terms of transmission? Okay, but this is the tendency. We know that the kind of computing power that we have now on a phone or a base station is going to increase heavily, and a base station is going to be able to see its environment. You have to know, today we don't see its environment. We measure CSI, but we're not able to see. Now with the frequency bands that we have, we can discriminate and do reconstruction of 3D with the base station of the whole thing. And we can run basically your EM equation solvers on the whole 3D map and be able to, with the texture that we do, things like that. I don't know if this can happen.
It's difficult. Yeah, it is true that if you use LIS or RIS, you can make a radar by doing multi-illumination, by changing the RIS configuration. And you can get a first image of your environment that after can be used in order to improve telecommunication. It may be the same RIS that can be used both to image and after to communicate, except you will use it in different configuration.
Yeah. So I didn't talk about this. I mean, it's not with LIS, but of course, in our community, a famous term is called EISC. It's been integrated sensing and communication. Which goes, so this is a heavy term which is being used in 6G, where you do both at the same time. How you do at the same time sensing and communication at the same time. I'm not a professional of that, but yeah, there's yes, there is yes.
And what is the increase in data transmission with ORM techniques? Really.
So
I have some doubts sometimes.
So just to let you know, there was OEM is not new. Okay, so it was there for years. In optical, they use it. Okay, optical people know OEM for years. Then there was some researcher from Italy. That's how it started. It's called spaghetti modulation. That's how, which dates back, I think, from 2012 or 2012. They called it spaghetti modulation, and they did something in Venice or Nice. In any case, they did a
we communicate between two.
And so they gave the claim things like that. Of course, everybody got excited about OEM and saying, "Oh my God, we have a new way of communicating. Shannon is dead. We're gonna do better than Shannon." By the way, we can do better by Shannon with this environment stuff that we're talking. I'm talking here about OEM. Then, of course, there's a paper from guys, and I worked with them from Sweden, which proved mathematically that MIMO in OEM setting does not bring you anything. Does not bring you anything in terms of capacity. So you cannot improve capacity with the OEM. It doesn't. But for us, it's very important is that if you have a large bandwidth, we don't know how to attack the environment with 8 gigahertz, 10 gigahertz in a line of sight things. OEM, that's the experience they did. Okay, if they were able to do classical.
It's a fixed beam for each frequency, and then you're going to adapt your emitter and the receiver to receive this sort of angle mode of your system. Exactly.
It's a way to use the large bandwidth.
Exactly.
But OEM in itself is not a breakthrough for me.
So it's the usage of these modes that with the boundary condition of your antenna, so you have a circle antenna on which you do it, and for which you're going to transmit. But yeah, there's no increase in capacity. So if I could do the DSP.
Recode your waveform in such a way that it's an angle mode of the system.
Exactly.
To minimize the complexity of the reception.
Yes.
And if you do MIMO, you have to do some processing, emission, reception. It's
Yeah. If I do MIMO system, I have a pure matrix, and I need to do some kind of what we call MMSC receiver or zero forcing. On the bandwidth that you have, we will never be able to implement it. So I'll never get the 1 terabit.
It's more a problem of bandwidth. Yeah.
Yes.
Okay.
However, there may be other features. I'm just telling you that in terms of, if you look just at capacity, it doesn't improve capacity. And the paper proves it. I mean, if you use MIMO with OEM. Now, if you use one antenna OEM, but one antenna OEM, you still need an array. So I don't know how you would call it.
You can make one antenna plus a surface that transform what comes from the antenna in
Yes.
good electronic design.
Yeah.
So we have one question online.
But you're right. In any case, the hype of the spaghetti modulation was during like 6 months or 8 months. I remember a lot of people were like, oh, this is the biggest.
So the question is, how do we see the role of noise and how we could take benefit of it, or do you think that it will be disturb more and more communication because of the increasing number of modulation, frequency, and even time varying materials?
So I don't know what kind of noise he's talking about. However, so there's different cases. The first case is modeling basically the lease and stuff like that, where you have no noise. The majority of papers there's no noise. It's perfect. If you start embedding things, which is also a culture that we had when we did relaying, because, you know, for us at the beginning, when we looked at lease, by the way, for your community, we were saying it's a relay which does flip and forward. You know, you flip and forward, which is something we know. Okay. It took us a bit of hard of understanding what exactly was your res or lease, by the way, because for us, relay, we know what is a relay, and it does either amplify and forward, decode and forward things. And already in the lease culture, in the relay culture, depending on where you have the relay, the strategy of what you do is different because of the noise. Okay, because the noise can amplify, and then you're just, of course, transmitting noise and not the signal that has embedded or something like that. So for sure, the problem with the noise is there, and for the moment, not many people are taking into account. Second, which people are not taking into account is that you're creating a whole interfering world in communication, meaning that you deploy one lease, yes, but if you start deploying many lease, this whole aspect, we don't understand how it's going to go. And this is going to be the second failure I talked about. The first one is deployment. Second is whenever you go to the agencies, INFR or something, and you start talking about interference, you know, you have these things, they're very strict. And then if you go into pushing it in terms of standardization or discussion, it takes a lot of time. People hate interference because they pay for the spectrum, they paid for dedicated bandwidth, they don't like it. So this is something that can happen also for him in terms of the noise level and things. But for the moment, I haven't seen so many papers tackling this problem. Other questions? Yeah.
Thank you, Mirwan. You mentioned all the hurdles to deploy at a large scale 5G networks and 6G networks. With your understanding of the maturity of the market, when do you expect the first large scale, ton scale deployment of these kind of networks?
So I take the case of 5G. So 5G today, so let's say one step by step, the guys were quite smart in deploying. So 5G today, the majority are deploying the EMBB scenario, which is the mobile broadband scenario, for two reasons. The first is they're deploying what we call 5G NSA. So NSA has nothing to do with the NSA. It means non-standalone. So what it means that you keep the core network over 4G. Today, the core network is 4G, and you only change the antennas and base stations. Because if you do that, the broadband is only the physical layer. You see, there's nothing which changes. Then if you want to embed the two other features, which are the most interesting stuff and where people think they're going to be the big business, which is the massive machine type communication, IoT, and second, ultra reliable low latency, you need to deploy a 5G network, which is called SA, standalone, where you don't use. So of course, the operator went jumping into NSA because today you can deploy a 5G network very fast. You just need to change the base stations, antennas, and that's it. Okay, so today, next year, normally, even at the end of the year, depending on the countries, you'll start having a lot of deployments of the full 5G SA standalone. Okay, On this 5G standalone, of course, the business of these two that I was mentioning is still not clear. Okay, and for which we could start making trials of much more features than what we had in the classical 5G. Okay. Second thing also, which is problematic, is the frequency bands. In the 5G setting, we have the C-band and we have a millimeter wave. In the millimeter wave, we don't know how to do mobile millimeter wave, because mobile millimeter wave supposes what we call beam alignment. We're not able to solve it. We're able to do fixed access in millimeter wave, WiMAX version. You send things, but we're not able to do mobile millimeter wave, meaning having a mobile and being communicated. Why? Because you need some kind of line of sight, and the beam alignment with the mobile, depending on where he puts it, is not easy for us at the moment. So this is also second step to make also the full potential use of the other bands that we have in scenarios which make sense for 5G. Because if you do fixed access for millimeter wave, I mean, I should not say this about 5G, but fixed access has been there for millimeter wave. You know what I mean? It's fixed access. It's all backhaul. You know what I mean? So the good part would be to use millimeter wave and the bandwidth in a scenario where we're mobile. So this is going to be increasing, and I think we will start seeing the full potential by 2024, 2025 of 5G, if you want things. Now, another question is, how can we import new technologies related to standardization in the 5G roadmap? Because if you want to do REIS, for example, this has to be done in 5G. It can't be done in 6G. It's too late. I mean, it's going to be 2030. You can, of course, trigger what would be the modification that you need to do in your REIS with respect to things to make the full potential. That's the research, and maybe impact the standardization in saying, we know that for REIS, what we need is a frame structure like this, because we need basically to update the changes every millisecond, or maybe it's every second. Okay, these things are something you can impact in 6G, because they will change maybe the frame structure, the feedback loop on which basically some signaling is going to be done, so that your lease can work at its full potential in terms of performance. However, if you want a direct use without impacting on the big potential, but see how it works, this can be done within the 5G frame, and starting to work with the people and make the changes minimal, which can be done in 5G. Because in 5G, you can still improve. I mean, standardization continues, but the changes are not, the physical layer is done. You cannot change. You can add some new things that could improve. And there, of course, things can happen in terms of improvements. Yeah.
Yes, a very pragmatic question. So if we speak about this millimeter wave stuff and access point extender we're working on, for example, in Japan, how long do you think the standardization can take on this very simple application? I mean, there's no interference or whatever. It's quite simple. How long is the standardization on this kind of stuff?
So on your experiment, I think if they're very active, they can push it within 1 or 2 years. Yes. Yeah, it could be pushed within 1 or 2 years. Yes, on this scenario. Yeah, it can be pushed quite fast. I think that the big issue that people will see is we have I mean, in the very example, relay, which is the starting point of a REIS, let's say, never kicked in telecommunication. This is something very important to analyze. We have some relay, but it's very specific to some cases. But we not have relays everywhere in the city to improve the coverage. And the main reason is still that as long as you don't control or you don't have access to the environment, people are very, back. So you will always have a push for specific things, and for very specific things you can negotiate. But the large scale of this deployment is, as long as I don't have that access to it, it's problematic, because it means I need to negotiate. We hate to negotiate, because negotiating means time. Many stakeholders, for example, base station, you cannot put it in front of a hospital. You cannot put it in front of a school. So, you know what I mean? So at least you'll get also people telling you, oh, what is this thing? Don't put it in front of a school, and you'll get, yeah, and then you need to go. So you need to have people who are very controllable. So of course you could go to the smart city stakeholders. So, for small cells, for example, we had work done with GCDeco, but even it didn't, because the idea was to say on all the bus stops, you have a screen, you can embed it behind the screen and put a small cell there and cover it. And there you have plug-in because it moves, so you have things, but even that didn't kick in. So then you need to discuss with some smart city stakeholders which have panels somewhere. And for example, JCDecaux could be a good company because they have these panels everywhere. And you tell them, oh, everywhere with JCDecaux, I will discuss how to put lease in every JCDecaux. Maybe. Yes, another question maybe.
Yes, Alors, what do you think about growing effort on 6G in the US, massive effort in China, and when we compare them to European efforts? Good luck for the answer.
My answer is I left Europe. No, I'm kidding. I think so. Two things. I think there are things that I didn't mention. Is what I showed until now around 6G is if history repeats itself. So, and what I'm saying by that is there are big uncertainties, and you're seeing everywhere for AI, for 6G, of what we call a sort of a digital or technological gap or division in the world. And so we're seeing it today. A single standard related to 6G is still a risk from my point of view, in the sense that we're seeing China moving forward and they're right and moving very fast. US trying to move also in the directions because of all the problem which started with Huawei and others, and where basically we're seeing some kind of digital gap between both. And this can happen, okay? Europe is trying to be in the middle of the situation because we're seeing China investing heavily. And of course, having two standards will be the worst case for us, because the benefit of standardization, I think you know all what it means. And so US a lot has been going, China I think is going on the classical realm of basically the classical standardization roadmap. US, we're seeing more the notion of what we call open RAN, open radio access network, which is basically the general idea that let's be open and have much more stakeholders working with us and starting to build that around. On the US front, this open RAN is still unclear because the problem is that whenever you have something, two things specific, that's the first thing. In general, you can optimize it. Whenever you have something very generic, things like that, in terms of consumption, it's bad. So we will lose a lot in terms of all these, because it means that you can plug this thing from that partner, that plug from partner. You're not constructing things. And you know, if you want to do an antenna, if you have full control, you can optimize the whole thing to have an energy efficiency of that number. So from that point of view, it's going to be bad. From the point of view of getting an ecosystem which is strong and also going faster, I think it's a good strategy, especially as they didn't have any big player. So going in the open RAN view is a fast way to go over there. In Europe, we're taking the strategy of still the classical approach of European projects. I think the investments are big, but not as what you would get in China today. With respect to what we were doing. But however, in Europe, the 6G realm went now. We have some good European project going on, but I don't think it's the right amount yet that we need to pour in to become a competitive leader, even though for some reason, which is still unknown, we have still two big players, which are Ericsson and Nokia, which are, as you all know, European. No.
Other question?
I think it's okay. Yeah.
So, thank you. I think we will close the.
Yes.
Meeting.